years already. We met in 2006 roughly, just after I finished my PhD at MBA, where he was staying for 6 months or something like that. And we were playing basketball in the summer of Munich. It was great. And Jesus got his PhD in Mexico, and was then a postdoc at MBA, and combined with Shanghai. So he had a 2-year period at MBA, and then also a 1-year period in Shanghai. And now the CITA National Fellow recently started in Waterloo, and he will be telling us about his recent paper on dark matter annihilation.
Thank you very much for being here. So yeah, I want to talk about this project that I have been working on for the last couple of years, and it's related to the possibility of dark matter detection through annihilation. So these are the people I collaborated with. And let me start just by giving a brief summary of why I think these candidates for dark matter are important, which are the so-called WIMPs, weakly interactive massive particles. They are, of course, very appealing from the point of view of dark matter because, well, they have masses and interactions of the order of the big scale. So when you take that into consideration and compute the abundance of these particles in the universe, they have the correct abundance or the order of magnitude of what the abundance of dark matter is. This is what is shown here briefly. Well, this is the commodity number density of these WIMPs. So the expansion of the universe is taken out of them. As a function of, well, we can take it as a function of time. This is the mass of the particle, the temperature of the surrounding medium. And well, at the beginning, the WIMPs are also in equilibrium with the rest of the universe. So they follow the equilibrium solution. But after a while, once the universe cools down, the process of annihilation of these particles, creation and annihilation is suppressed, and you essentially have a fixed amount of WIMPs, which corresponds to a fixed amount of dark matter, and it has the appropriate value as we observe today. As you increase the probability of interaction with these particles, of course, you reduce the abundance of them. So again, they give the correct abundance of dark matter, so that's one of the reasons why they are called the WIMP miracle. But it's also, they are also appealing because they arise naturally in other models that go beyond the standard model. So they have a theoretical reason to appear. So one of these is through supersymmetry. One of the most favored candidates is the neutralino, which is perhaps the most historic one. And I just want to say that this particle, the neutralino, it also has all the other properties to be dark matter besides giving the correct relative density. It also behaves as cold dark matter, which is the current paradigm of structural formation relies on cold dark matter. So neutralinos also behave as cold dark matter. And the other two properties that make it very appealing, also in my opinion, is that they have the possibility of detection through non-gravitational means in the near future. So they can interact with ordinary matter, although very weakly, and they have a very nice property for detection because they can self-annihilate. So they annihilate themselves to produce the standard multiparticles that we can see. And that is why people have been trying to detect them, to look for them here on Earth. So these are called direct searches of dark matter. And there are several experiments now going on Earth trying to look for the signals. For example, the DAMA experiment or the CDMS in the US, the xenon in Italy. And actually, well, DAMA is one of the most controversial ones because it has detected a positive signal, but none of the other experiments seem to agree with this. So in this plot, you can see the cross-section. This is the cross-section not for annihilation, but for interaction with nuclei. as a function of the mass of these particles. Here in red, also these violet regions, is more or less what you expect from these supersymmetric theories, where these particles should be located. So it has a very small cross-section. That's why this is called the septobarn scale, which is 10 to the minus 45 centimeters squared. And the importance of that scale, because once experiments reach this level of sensitivity, many or a lot of the parameter space will be able to be ruled out, or it's at least in the interesting region for these supersymmetric theories. So right now we're something around here, and 5 or 10 years we'll be able to reach this level of sensitivity, which would be great for a possible detection if that matter is made of these supersymmetric particles. I just want to stress that it's important to mention that all these experiments depend on what's the actual distribution of dark matter within near the Earth. Also, it depends on the flux of dark matter in the Earth and also what's its velocity distribution. So there is another possibility of detecting dark matter. So that's looking for, as I said before, they have the property of annihilating themselves and produce standard model particles like positrons, neutrinos, or photons, among others. And so if we look at the sky and we see an excess of these particles that we cannot explain, perhaps this is caused by dark matter annihilation. There are also several experiments not really dedicated exclusively to the search of dark matter. They are there for other reasons, but they offer perhaps the possibility of detecting dark matter. Like the Pamela experiment, which is very famous because it detected this excess of positrons, so excess of positrons in cosmic rays at high energies, which might be a sign of dark matter annihilation. You can also have neutrinos, extra neutrinos coming from the sun, because the winds can concentrate gravitationally inside the sun and then annihilate, produce this excess of neutrinos. You can also have photons, which is what I will concentrate on the rest of the talk, and the Fermi satellite, which is mapping the sky in gamma rays, offers this possibility of detection. So how do you get the photons out of the annihilation? Well, in general, the emissivity of the annihilation depends on the density of WIMPs, the density of dark matter, squared. Why squared? Because you have your target and the particles that are hitting the target are the same, again, because they self-annihilate, so that's why you have the square here. So this part of the emissivity depends on how dark matter clusters gravitationally. And then you also have another part that depends on the intrinsic properties of dark matter as a particle, which is basically its probability of interaction of annihilation, which is just cross-section, its mass, and the number of photons, in this case I'm talking about photons, that are produced per energy in each annihilation event. So I find it nice that you can analyze these two things more or less separately, and it's perhaps easier or better to understand it in that way. Again, as the dark matter as a gravitational particle and dark matter as a particle itself. So I will talk about both of them separately. So how the photons are generated in this annihilation process? Well, there are three main mechanisms. The most dominant one is this one. You have the WIMPs. They annihilate and produce a pair of quarks, a quark-antiquark. And then this pair hadronizes to produce, for example, pions, neutral pions, among other things. And then these neutral pions decay eventually, and they produce gamma rays. So that gives you a continuum spectrum that goes from the mass of the neutral pion all the way to higher energies onto the mass of the of the particles that are annihilated. You also have another two ways of producing photons that, although are subdominant, they are important because you see this mechanism is very similar to other mechanisms. So the spectrum will look the same if you have other ways of producing these spirals. However, these two, they come directly from the annihilation of WIMPs. So for example, this one gives you directly gamma rays from the annihilation of the particles. And because it's a direct process, it has the energy of these photons have the mass related to the mass of the particles that are annihilated. So you really have a line in the spectrum that tells you what's the mass, or can potentially tell you what's the mass of the particles that are being annihilated. So this is called like a smoking gun signature. This is another interesting one. So whenever these particles annihilate into charged states, there is an additional photon that's produced in this way. It's called internal remsharing. So we have these three mechanisms to produce directly photons, but you can also affect other photons that are there in the universe. For example, you can take background photons, and when they interact with some of the particles that are producing the annihilation event, they can gain energy for inverse quantum. And you have essentially, you change the population, for example, with the CMB photons. The CMB photons collide with the electrons and positrons that are produced also in this annihilation event. And these electrons give energy to the photons. And so you can transform lower energy photon into a high energy one by this mechanism. So annihilation also can be perhaps detected in this way. So this is how the spectrum looks like for an annihilation event. So this is just the number of photons produced per energy range. I have multiplied it by energy squared. It's a function of energy. And here in red, you see the first three mechanisms that are described. So, so in red is the photon that I call prompt emission. So they come immediately after the annihilation. And so you have this shape. This first part is just this continuum of the decay of the neutral piles. And then there is this bump that's actually related to this internal Remshaven. And there's a line there also, which is very hard to see, but the line tells you this direct annihilation into gamma rays, and is essentially centered at the mass of your WIMP, of your annihilating particle. So this is just the example that I'm taking. So it's a wave of the order of 200 gigaelectron volts, decaying to bottom and anti-bottom quark. This is just the order of magnitude for the. So this is just an example to tell you how the spectrum looks like. So what happens with the other secondary photons, or these photons that are the CMB photons that collide with the electrons and positrons? So in dash red, this is the injection spectrum. So the particles annihilate and produce electrons and positrons. So you see it looks very much like the photon one, because it's essentially a very similar process. In this case, the charged particles that decay to produce these particles. So once it interacts with the CMB photons, it reaches these electrons and positrons, lose energy, and reach an equilibrium spectrum, which I have plotted here. It's not normalized, by the way, but it has this shape. And it has, it produces, it changes, or it produces secondary population of photons at lower energies, which is marked in blue, which are these CMB photons that are gaining energy through this mechanism. So now I will talk about the astrophysical part of the signal, which is this density square dependence. So any region that contains dark matter, then these scenarios will annihilate and produce these photons, and well, it will be just given by the integral. So the part that depends only on the way the dark matter clusters will be given just by the integral of this quantity. And you see, because of the density squared, is more promising to detect perhaps annihilation in regions where dark matter is very dense, like the center of our own galaxy or in satellite galaxies that are nearby. Well, there are, of course, active searches there, and although they have some problems, I will talk about them here. I will just concentrate on what happens when it's outside the galaxy. So outside the galaxy, there are many halos of dark matter and different structures that can also give a signal. So just to give you an idea of how can you expect to compute these signals, well, you know more or less with accuracy how dark matter is clustered using n-bulk simulations. So this, for example, this is taken from the Aquarius project, a very large simulation project of a Milky Way halo. So this is a halo of 10 to the 12 solar masses, so the order of the halo of our own galaxy, and it reaches resolutions of the order of 1,000 solar masses. And well, this is how our own halo would look like in the sky if the annihilation exists. So something very concentrated in the center and then spread out. And when you compute the total luminosity coming from this halo, you see, even when the simulation is very high resolution, and you use the particles, the density that is given by the particles in the simulation to compute the total annihilation in this halo, it's actually pretty nicely expressed just by scaling law. So if you just know what are the global properties of your halo, you can express the total luminosity of this object, just essentially given by the mass of the object. So that's nice that you can use this, because then you can assume that these high resolution simulations can be applied to other simulations of lower resolution, and just use these kind of scaling laws, and you will be safe from resolution effects that you would be that would be present if you would be using the particles of the simulation. It's much easier to use the halos themselves that are in the simulation, but they don't have these resolution effects. So
also the definition of R max and R max.
Yeah, I'm sorry. So this is the rotational velocity at the maximum, and this is the radius where it acquires that velocity. So this formula is good because, as I said before, usually you have a simulation, you have the particles there, but you have resolution problems, especially in the center. So I'm talking about a cosmological simulation that we will use in this project. So in them, you cannot rely on the particles' densities because they are basically not resolved in the center. So it's better to use this kind of formulas. Of course, dark matter halos are not smooth, so this was just assuming that dark matter is distributed smoothly in a halo. But they are they are full of substructures inside, and these substructures are actually very important for the signal because they are very dense structures and they are very abundant, so they can produce signal that actually is dominant over the signal of the whole halo itself. This is what is shown here. So this is just the luminosity as a function of radius, the cumulative luminosity, normalized to the luminosity of the whole structure. And the red line is the profile that you expect to see if dark matter was just this smooth component. So the substructures were not there. And you see it's very, again, it's very centrally concentrated. You have around 2 kiloparsecs or so, you have already 50% of the total annihilation comes from the 2 kiloparsec region. Just as a way of showing this is the blue line of how concentrated it is the mass profile. So you see 50% of the mass is not acquired until really 100 kiloparsecs or so. So much more concentrated how the mass is used. Now the subhalos, these are the green lines. The different green lines are different mass cutoffs. So this is considering subhalos tend to be 8, 7, 6, and 5. And you see how, as you consider less and less massive subhalos, the contribution of subhalos first is very much less concentrated than the contribution of the new component. So it's basically, so halos are located in the outskirts of the halos. So you have a lot of them here, and they produce, at this level, they produce a luminosity which is of the order of the luminosity of the whole halo. But what happens, we know that these simulations cannot resolve all the hierarchy of the structures all the way down to, let's say, 10 to the minus 6 solar masses, which is what we expect from the current paradigm of structural formation. So that's of the order of 1 Earth mass. So we cannot hope that the simulations will achieve that resolution. But if you see, these shapes are more or less invariant of the scale that you are taking for the mass of the subhalos. So you can make the exercise of extrapolating this and say, okay, if this behavior continues for lower and lower masses, how much signal or annihilation I expect from this substructure? And you get something that is like 200 times more than what you expect from the halo itself. So all of this is just to tell you that substructures are very important, have a very important role, although it's still uncertain really how that role is. We expect that it will be at the level at least of the halo itself, or really much larger. So what we did in our project was to say, okay, so you have the halos and we produce this annihilation. So what would be the total integrated signal coming from the halos that are outside our own, along all our past light going. So all the structures, all the cosmic structures that are sending these photons and are hypothetically reaching us. So what's the signal to that? And how can we use the simulations and the knowledge that we have of this part of physics part of the dark matter to produce this, predict the signal. So this is just the specific intensity, which is just the integral of the visivity, how many photons are produced per annihilation events. There is, of course, some of these photons will be absorbed in the way tower source, but only the very high energetic ones. So we want to use the simulations to make this prediction. So we'll use a cosmological simulation that I will show in just a minute. And again, instead of using the particles themselves, the local density that the simulation gives us, we will use the global quantities of the halos to compute the luminosity.
What absorbs the photon annihilation?
I'm sorry?
What called photon absorption?
Yeah, so the photon absorption is essentially caused by pair production. So these are 10 gigaelectron volts and higher photons, and they produce pairs, so they are basically absorbed. So this is the simulation we use. This is
what is the pair producing also? The pair producing of the infrared background? Or?
Yes, all the backgrounds, the starlight background.
So you're talking about 1 TeV or 10 TeV center mass frame annihilation, right?
Well, you actually have depends both on the energy. So these photons, since 10 gigaelectron volts up, they can be absorbed at 100 gigaelectron volt energies or so.
Right, but you need 100 gigaelectron volts is transparent, more or less. Right, so you need like almost like 10 EV, I think you need something like 10 EV photons, and that's UV photons.
No, you're right. It's just that once these photons that are very highly energetic reach us, they will be redshifted. So you will receive the energy the observed energy of 10 gigaelectron volts that you observe today is probably produced at redshift 5 or so, which is more energetic.
Okay.
So this factor just accounts for that. But it really affects only the very more energetic photons. So this is the simulation that we use, which is an MPA project. It's called the Millennium 2, which is a follow-up of the Millennium 1 simulation. It's using the same cosmology, the same number of particles, but the box is smaller, so it has higher mass resolution. This is just a snapshot showing how this dark matter is clustered and at different zooms. So this is just zooming on a very massive cluster at different scales, so you can see the level of resolution that this simulation can reach, which is something like 10 to the 8 solar masses or so. It has, of course, a lot of subhalos and halos. So we use this simulation to we use the information that we have from the simulation for how the structures form and evolve to produce this prediction. So how do we do that? We need to simulate the light cone towards the past. So what we do is, so we locate the observer there and we separate this by this light cone in different shells according to the different outputs of the simulation. So the simulation can give just a discrete sequence of the evolution of these structures. So at each output of the simulation, you will be able to simulate a given volume of this light cone. And what we do just to, this is just an extra step that we do, so we fill this volume by replicas in this box within the whole volume. And each shell, for each shell, we translate and rotate to avoid having the same structures along the line of sight. This is just to avoid having essentially the past of these structures along the line of sight, which we will be, of course, fully respect. So once we do this, we can produce maps. So basically, you take a given angle on the sky and compute what's the specific intensity, what's the signal that you are getting from that angle on the sky, which is just the sum of all halos and subhalos that we have on the line of sight, all the signal that comes from there. And what is weighted by this particle physics part that depends on how what candidate or what model are you using. And this is how the map looks like. Just the central part, so just this very first shell, you can see just 68 megaparsecs or so. This is how this will look like. So you have some sources that will be resolved, so these halos that are very close by, and another ones that are really point sources. So you see, you can appreciate how the local structures are clustered near the observer. But this is just the first shell. What happens if you integrate the whole signal? Well, this is what you get. So it's a much more smooth map. So this is all the way to ratio 10 at an energy of 10 gigaelectron volts. So this is very, very, very smooth. And you barely see, you have a couple here, you barely appreciate the local structures, and this is because the signal is dominated by low mass halos that are relatively far away. So you see essentially an isotropic distribution, although the anisotropic of this is important, as I was saying before. So just let me tell you, as I was saying before, so structures are very, very important. And we expect for this kind of candidates and WIPs to have the masses that survive, the minimum masses that you can have these halos, gravitational bands of the order of 1 Earth mass. So once you take that into consideration, that of course you don't resolve the simulation, you can expect something like 2 orders of magnitude of uncertainty of how these structures can affect or contribute to your signal. So this is something important to keep in mind because this is the uncertainty level that we have on that. So what happens if you do that for different energies? So this is the spectra of this specific intensity of the signal you get from dark matter annihilation as a function of energy. It's this gray band. So again, this region brackets this uncertainty on how subhalos contribute to the signal. Minimum contribution, maximum contribution. And you see the shape is the characteristic shape that I showed before of CND photon being upscattered by electrons and positons of the annihilation, and this prompt emission, gamma rays that come directly. Together in this figure, so by the way, this is again the same example that I gave before. In this figure, you can also see different measurements of this cosmic background at different energies by different satellites, from Chandra to Fermi. So it covers a large energy range, broad energy range. And the points are absolute measurements of this background that we have reported along the years. The arrows are upper limits on the contribution of sources that are unknown. So here we think that ADN are responsible for these X-rays, background of the X-ray. So the signal is, the extra contribution is suppressed. And here at higher energies, we expect blazars and star-forming galaxies that also can produce gamma rays from different mechanisms. They are expected to contribute at different levels. So in particular, blazars, the 16% has been estimated recently. So this is really blazars that are accounted for by the Fermi group. It's something like 16%. For the star-forming galaxies, is much more uncertain. Here we are assuming something like 50%, which could be high. But I will comment on that later on. So the important point to make is that here you have a very constrained possibility for these models. What you see is exactly more or less in the region where these models peak. This of course depends on what particle physics model you are using. But as I described in a couple of slides, that can be more or less taken care of. The important thing to take here is that this gives perhaps a very powerful tool, not perhaps to detect dark matter itself, but to constrain the different possibilities. So just to show you how it depends on the different annihilation channels. So the model I showed you before is something similar to this blue one, which is bottom, anti-bottom. But you can have also other models where the annihilation, for example, happens directly to electrons and positons. And of course then, the majority of the signal comes from this inverse Compton scattering that we see in the photons. You see here is very large, so this will be the dominant signal. So although X-rays at this moment, as you can see here, are perhaps not very constrained, if you have a model that fits here, well, that will be important. And also, the contribution of other sources like ADN is more known perhaps here than how the sources contribute here. So as I said, you have in this plot, you have both the particle physics part that tells you how the spectrum looks like, and also the astrophysical part that you have dark matter clusters. But you can take just there's a price to pay, but you can take out from this integral, the specific intensity, you can take out the part that depends on the particle physics. And when you do that, then you are just left with something that depends on the astrophysical part, and that is given more or less accurately by the simulation, with this to orders of magnitude uncertainty to how scales contribute. And the rest depends on particle physics properties. So you can ask yourself, what's the maximum, or what's the spectrum that I need to have to match this missing contribution? And that's what I did here. So this is the part that depends on the particle physics. So this F width is just this quantity here as a function of energy. And the gray band tells you that everything above this is excluded by the constraints of these different components. Depending on if you take minimum or maximum, or this can go again towards magnitude or so. So this plot is nice because then you don't need to do all this complicated procedure of using the simulation to do the maps. You can simply take your preferred model of particle physics and plot in this plot and see if it passes these constraints or not. So that's something that we find is very nice. So once you have chosen a particle physics model, then you've chosen the spectra that was inside, and then you can put these constraints as a function directly of the cross-section and the mass of the particles. So that's what I have done here. This is another example. This is just annihilating into muons, which is, I chose it because it's usually has a spectrum that is used by different people to fit something like Pamela. So in that case, you have to, or you want to produce this excess of positons, and this kind of model gives you that. So this violet region is the models that fit the Pamela data. And again, gray regions are excluded, so this is really when subhalos almost don't contribute at all. So this is, I would argue that this is the minimum case. So everything should be, in reality, you're probably here somewhere. And again, you see that there is just a small window here for this kind of models to explain Pamela completely just with dark matter annihilation. So these constraints are powerful. That's what we are finding. Moreover, we do an exercise with more with models that have been proposed recently and that are more sophisticated and that can fit the Pamela data as well. So these models, there is a new force carrier that is introduced in the dark sector. So you have a theory where dark matter is in a hidden sector, and in this hidden sector you have a new force carrier that interacts or that acts between the particles in this dark sector. So once you introduce this new force carrier, you have to first, your annihilation cross-section can be enhanced by something called by a Sommerfeld mechanism, which is essentially rises the annihilation cross-section, and this allows you to get very high cross-section and then fit things like the Pamela data without violating other constraints. So these models still give you correct density, although they have high cross-section, they are able to produce the correct abundance of dark matter. They also fit, as I was saying before, Pamela and Fermi. They are also allowed by constraints on the CMB because the CMB at the time of recombination can also be affected by annihilation, because annihilation injects potentially energy into the photon boundary plasma at those times, and you can change the angular power spectrum of the CMB. So these models, all these 6 benchmark models that were proposed recently, they pass all these constraints, they fit the Pamela data, and we wanted to check if they also pass our constraints. And the answer is they don't. I would say that a little bit more about that. But, so this is essentially just the observed value of this the wind factor divided by the ratio of the wind factor according to the model. So anything above 1 is essentially ruled out by the constraints. So here you see the model, the low one is ruled out. So here the models, all of them, so these are the 6 benchmark models that I described, which are, by the way, are very similar photon spectra, are ruled out. So this is perhaps a factor of 10 or 5 or so. Again, I've done this with a minimum contribution from subhalos, so there is not much room there. But I have to say that I put 52% of the star-forming galaxies in the signal, so that's perhaps high. Blazars 16%, which is, I think, okay. But again, this number could be very high, so what we did was to explore what happens if you reduce that number. So essentially what happens if star-forming galaxies don't contribute as much as we think, or as much as this number. So this is how essentially how the cross-sections, you can translate this into an upper limit of the cross-section. And in this kind of models, by the way, these are the colors of the model just as a reference, as a function of the contribution of star-forming galaxies. So in the model we had something very high, something around here. But let's say it's even 5%, or even 0. Then it will be somewhere here. I mean, these arrows indicate the cross-section that these benchmark models use to fit the Pamela data. So you see, even by relaxing, by saying that star-forming galaxies don't contribute basically anything, these models are still too high. You know, this line will be somewhere here, and we need to be somewhere here to fit Pamela. So our results seem to indicate that you can, they seem to disfavor an explanation of the pamela excess just by that annihilation. So, as I was saying before, I want to talk now about what happens with the anisotropic that you see in these maps. I said earlier that they are very smooth, but even then there's of course some degree of anisotropy there. That is interesting because they can tell you something of the process of annihilation itself. The spectrum doesn't tell you much because there are other things that are producing the energy spectrum, but the power spectrum or the way the anisotropies of these maps perhaps contain more information on the annihilation process. So what I did was just to take those maps and compute the power spectrum and just concentrate on the red line. So this is essentially the case where Zavala dominate the signal, so it's maximum case. You know, at small multiples, so these large scales, the spectrum is given essentially by the distribution of halos in the sky. But as you go to smaller scales, you start reaching the inner structured halos themselves. So here's subhalos dominate the signal. And because halos are less concentrated than dark matter itself, you have somehow a flattening here of the power spectrum. As you go to even smaller scales, the power spectrum is then dominated by the low mass halos that are basically the dominant feature in the small scales. And that's, again, clustered almost in an isotropic way. So that's why this goes almost as L squared, which would be something that is randomly distributed in the sky. But I have something that, this flattening, to tell you something, is something particular of the annihilation process. So now the power spectrum has also another nice feature, is that it depends on the energy of where you observe it. So this was at 10 gigaelectronvolts. But if you take the power spectrum of different energies, just because different energies tell you something different about the spectrum of the particle physics model, then they will also produce a different power spectrum. And essentially what you will have is that, so this is the power spectrum of different energies compared to the power spectrum at 10 gigaelectronvolts. Different cores are different energies. The lower energies, you have a power spectrum that is lower in normalization than it is at 10 gigaelectronvolts. And this is just basically because at lower energies, your signal depends more on higher redshift halos or structures. And at higher redshift, you have less clustering. So that's why you have this suppression. But you see, there are also changes in the scale, not only in normalization, but on the scale, on the angular scale. And you can explore these changes to do something nice, which I will show now, these color maps. So what I did here was to take maps at different energies. And as I have repeated several times, when you just take the maps at different energies, they look very smooth. So here I just moved to I think it was a 5 degrees filter. And you see they are very smooth. Before. You see a couple of structures somewhere there, but generally you don't appreciate the structure there. But what happens if you take the map ratio to, because of this difference of the power spectrum of different energies, see how the structures are the local structures are highlighted in this kind of maps. So you appreciate more how dark matter is distributed. And just to show you that more clearly, this is the ratio of the maps, and this is a map just at the first shell, at redshift 0, so really the local structure, at a given energy. So this really just is essentially by default tells you how dark matter is distributed just around us. And you see when you compare these two, so this would be something that you can potentially make from observations directly. It's something like Fermi. You compare these two, you see that they more or less have some features that are recognized from both. So again, you can use these map ratios to perhaps map the local structure, so, which is, I find something very nice. So just to end, so this is some summary and conclusions of this project. And it's very nice because it combines particle physics models and the information that you can get from simulations to get, I think, very accurate predictions, although you have this degree of uncertainty, but it's an uncertainty that you know that is caused by your ignorance of how cicadas contribute to the signal, and you can use them as a tool to rule out models, perhaps at the level of the isotropic component, not to claim a signal. I think this is very hard because, as I said before, perhaps the dominant sources of the signal are others, for example, lasers or star-forming galaxies. But if you look at the anisotropic component, there's a possibility there of seeing that one annihilation. And the scholar maps are very nice. And again, we're reaching perhaps a level where you can use this isotropic component to rule out other models that could fit things like Pamela, etc. And also the technique can be used to model perhaps the other sources in different ways. So
Questions?
Can you comment on how you got 3% for the star-forming contribution?
yes, so there are different, I took a model of Anglo and Pablo. So what they do is essentially, what you need is the star formation rate, it's a function of redshift, and you need also have the number density of galaxies also, and then you cobalt that. So from star-forming galaxies, what you have is that the cosmic rays interact with the interstellar medium, and they, by proton and proton collision, you produce spirals and spirals decay. So what you need is a way, or you need to understand how star formation rate evolves. So that's what you get. Now I took 52% because this particular model uses 52% as their best estimate according to how the star formation rate evolves. But this is of course controversial, so that's why we reduce this number to zero, essentially, to see how much.
I guess the photon spectrum is dependent on mass distribution, mass spectrum of the dark matter. Right. Then how do you use what distribution, mass distribution of the dark matter particles?
Yeah, I mean it depends. More than that, it depends on the annihilation channel that you have. So you have you pick a particle physics model, and then you have different possibilities for that annihilation channel. If you pick a supersymmetry model, then those annihilation channels are just given by, the Feynman diagrams of the theory that tells you, okay, this will annihilate to this, and that. And then with that, you can produce, there are codes to produce the spectrum. Or you can simply say, take your own model and say, my model will annihilate into quarks or into electrons, and then you will give you different the photon spectrum.
Another question is, in the PEVs and MEV band, it seems that the model prediction is very different.
Yeah.
What do you do?
I mean, so this is, so again, if you go back to, this one. So that first that you see at X-rays is just this inverse complex scattering you see in the photons. So this will depend essentially on the injection spectrum that you have from the annihilation effect. So this is also, you have the annihilation channel, and then you have different particles that come from the different annihilation channels actually. So in this case, it's actually very similar to the one that comes from gamma rays. But then this spectrum, what you actually want is not, of course, the electrons and positons. What you want is the spectrum with the photon component, essentially the CMB photons. This is the one that we should be found. So the CMB photons are raised to energies of the other X-rays.
Oh, okay, so you mean the green region, shaded regions for the one chamber, not from the upscattering of the CMB.
Yes, so you have so depending on the mass of the particle and its annihilation channel, you can have, so here this particle has 200 gigaelectron volts. So most of its spectrum is here, centered here. So these high energies will be transferred, some of that energy will be transferred to the CMB photons, and the CMB photons have lower energy, but they gain energy to this mechanism and it breaks to this level. It can even be more. No? So, for example, if your particle is more massive, then that spectrum will be more to the right, the injection spectrum, and the CMB photon will peak around, you see here it peaks around 1 gigaelectron volt or so. And this is the same inverse quantum signal than this one, but the annihilation channel is different. The mass of the particle is different, and that's what produces the difference between these two.
Okay, I guess we can stop here and go out for cookies. Let's thank our speaker again.